Today we will learn how we can build the end-to-end RAG pipeline or RAG system. We'll see what are the different components of RAG, and we'll start building the basic RAG pipeline, and then we'll iterate towards building the advanced RAG pipeline with high accuracy. So the first question is, what is RAG? So RAG is a technique for enhancing the accuracy and reliability of GenAI models with facts fetched from external sources. So in simple terms, so whenever we ask a question to large language model, we provide the context also to the model and ask the model to give answer from this context only. So that is RAG. Now, so in our case, we'll building this RAG pipeline on PDF. So this is a PDF document which we have, where it consists of all the current affairs for last 6 to 7 months. We'll ask different questions from this PDF file, and we'll let the model answer this question from this PDF only. So let's get started. So RAG consists of two important pieces. So first is the retrieval part, second is the generation part. So in simple words, retrieval helps us finding that relevant context which we can pass to the LLM, and generation is mostly the large language model, where we pass the prompt, the question, and the retrieve context, and ask the model to give us the answer. So let's dig deeper into this architecture diagram. So first, we take some external sources. So in this case, we have a PDF file. We process the PDF file. So while processing means we create different chunks of the PDF. Then we pass this chunk into the embedding model, and using the embedding model, we create different embeddings for different chunks, which we store in the vector DB. And when the user asks a question, suppose one query comes, using the same model, we create an embedding, and then what we do is like we do a embedding search into this vector. So we do a cosine similarity search for a given query. What are the relevant chunks available in this vector DB based on the highest cosine similarity, and we retrieve like top 3 or top 5 results back, and then that information is passed to the large language model, which is like prompt plus the query and plus the retrieve and ask context, and then large language model use this information to give us the answer, which goes back to the user. So this is the high level architecture diagram of RAG. So let's move further. So first, to run this notebook, we need GPUs. So either you can use Kaggle free GPUs, which is like GPU P100, or you can use Colab free GPUs also to run this notebook. I will provide the link of this notebook on GitHub, and you can just download this notebook and run wherever you want. We'll start with installing the required packages. So I've used Quite here, which so will not show the progress, but yeah, it will get installed. And then we'll download the data. So we'll download in the same PDF file which I showed here. So this is the PDF file we are trying to download using this command, and I'm just storing in the data folder. Next is let's import all the required packages. So I've imported all the required packages here. Then what we're doing, we are just loading this PDF file using this PyMu PDF reader, and then we are just taking a content out of it, storing in a doc text, and then wrapping it with a document class, and then storing everything into a docs list. Loading the data, next we will download the large language model. So we will use Zephyr model here, and we'll use HuggingFaceLLM API to download the model. So this is the API. You just have to pass the model name, tokenizer name. We have to give the query prompt template also. So this is template. This is the input query which will be passed from the user. It has a context window of 3900, so it can take an input of this much size. Max new tokens means like what is the output token limit. Model cogs. So not only we are downloading the model, we are quantizing the model also, means we are reducing the size of the model. We are using 4-bit quantization so that we can run the model in the 16 GB RAM. And the other parameters which we are using for model is do sample false, which means that we don't want sampling. We want that every time model should take the next token with the highest probability. So like a greedy decoding. And then we are passing the message to prompt, which is this one. And device map is auto, means it will choose whether we have GPU or not. So next we'll download the embedding model, which is a BG based embedding model we'll use using the Hugging Face embedding API. So in Hugging Face we have an embedding leaderboard which we call MTB leaderboard. So there you can see different embeddings available and what is the performance. So BG base is quite a good performing embedding, and the size is also low less, so I think that's why I'm using this. So next is now we have the document loaded. What we want to do is like we want to create a chunk out of it. So we'll use SentenceSplitter. It will just split the document into different chunks. It will just try to keep sentences, paragraphs together. So by default, the chunk size in this splitter is 1024 and overlap is 200. We are using the same setup. And then so we are creating object node parser from this sentence splitter. Then what we are saying is that get nodes from document. So what it will do, it will take the all the document and create different chunks using this sentence splitter. And in LlamaIndex, all the chunks are referred as nodes, so they are saved as nodes. So if you want to print the node value at first index, so this is the node which is a text node. The ID is this. It has a text which is given here, and there's other relationship which LlamaIndex keep, like what is the next node ID, what is the previous node ID, which can help Llama in traversing. So if you want to print the text, you just have to do dot text. It will just print the text. So next is so there's one silent issue which we got, which for which we did not get the error also. So the issue is like we have created a chunk of 1024, but the model which we are using, the embedding model BG base, has a token limit of 512. So what it will do, it will, while creating embedding, it will just use the first 500 tokens only, and it will truncate the rest of the text. So the quality of the embedding would be low. So let's investigate like how this truncation happens and why we are not getting this error. So what we'll do is just take the embedding model and then use the underscore tokenizer.encode method, which will take the text and truncation as true. It will give you the tokens. So this is the token we got. If you see the length, that we have got 512 tokens, so it has just truncated the text. So out of 1024 we are getting only 512. Now if you want to just decode back and see where it has truncated, so you can just use decode method and it will give you the text back. So if you see, it has truncated, like, or it has used the text till people with high blood sugar .mil. So if you see the text, you will find this somewhere here, like people with high blood sugar .mil. So it has just used text still here. After that, it has just truncated, like everything is truncated. So always just make sure that whatever chunk size we are using, it should be less than or equal to the embedding model max token limit. You will not get an error, but it's a silent issue, and which degrades the quality of the context embedding which we create. So next is service context. What it does is like it just wraps your LLM and the embedding model and creates an object of it. So we have just created that. Next is VectorStoreIndex. So this is where we store all those embeddings and the chunks. So what we have to do is like we have to pass all the nodes into this VectorStoreIndex and the service context. And what it will do, it will take use the embedding model of this from the service context, and will create an embedding for every chunk, and it will store in this vector index. Now we can use this vector index as a query engine and provide, like I'm giving top symbol similarity top k is 3 means it will give me the top 3 matching answers. So how it works is like for a given query will just create a embedding of that query using the same model, and then based on the cosine similarity it will try to find the top 3 similar chunks from this vector store, and it will give me the top 3. So you can choose top 3 or top 5, whatever you want. This is a parameter which we can play around. So we have created an instance of vector query engine. Now what we'll do, we'll just test our RAG system with this setup. So I've chosen 5 different questions from this PDF document. The first question is, what is the country? Which country is the largest producer of millet? So if you see, I think it should give the answer like India is the largest producer of millet. So let's run. So what I've done, I just loop all my questions and passing each question one at a time in this vector query engine.query. It will take the question, create an embedding, then it will just do a cosine similarity of that embedding with the chunks embedding stored in this vector store, and it will give me top 3 results as a uh, context, and then those top 3 results with a query and the prompt will pass to the large language model, which is defined in this service context. And then large language model, what it will do, it will give you the final answer by just going to the context and the query. So let's see what output we got. So first question was like, which country is largest producer? India is the largest producer, so it gave us the right answer. But for rest of the questions, if you see, it did not give right answer. Like for this question, the saying it does not mention this word or the scheme. Initiatives proposed in budget to eliminate anemia by this. It's saying that the specific norm of the initiative is not mentioned. And then what is the median age of India, China, and Germany? So that is also it's not able to give correctly. But yeah, last answer it could give correctly, like 559 crores is the allocated budget for natural farming. So with this setup we got only 2 answers correct, but we know the reason because the chunk size what we chose is 1024, and the embedding what we got is not high quality because it's just truncated the of tokens to 512. So what we'll do next is like let's change the chunk size to 512 in our sentence splitter, and let's keep everything same. So just again create a node parser by passing chunks as 512. Then again I'm creating vector store, parsing the nodes and the service context. This is my new vector store names I'm using as a query engine. I'm again asking top 3 only. And what we will do, we will just again run the same thing, run all this question to this vector new vector query engine and pass one query at a time and see what answers we are getting. So first again it's giving the right answer. This is still not giving the right answer. Third one, which initiative? So initiatives like sickle cell anemia, got it correctly. This one is also like correct. Median age in India is this issue. So you can verify these answers in PDF. I've already verified, so I'm saying, and yeah, this one is also correct. So it's just by changing the right chunk size, our performance improved drastically. Now out of 5 we are predicting 4 correctly, so like with 80% accuracy. So yeah, just doing basic things right, we can improve the performance of our RAG system. Next, what we'll do, we'll try to debug further, like why this second question is not predicted correctly, like why we did not get the answer. So the issue is from LLM side or the retriever side. So what we'll do is like we're using the same vector index 512 what we created with this 512. What now earlier we used as a query engine. So now what we'll do, we use as a retriever. So what it will do, it will just for a given query, it will give you the context information, which is then passed to the LLM. So we are again saying top 3 we want, and then we are saying vector query retriever dot retrieve, and I'm just passing the question and like the second question to this to get the context. Now I'm just written a function which will check whether this word samagra is there in this text or not. So it's clearly says that no, it's not there. So what does it mean? It's like it did not retrieve the relevant context from the PDF which can answer this question. So if you search in the PDF, there is a scheme, like Samagra Shiksha scheme. So ideally, you should have found this context as the top three contexts, and it should have given or passed to the large language model. So now the question, like, why we did not get that chunk which says about Samagra. So if you see this question, there are only three important tokens, which is one is Samagra, second is Siksha, and third is scheme. And out of these three, if you see, scheme is the only popular English word, rest, and which will be present in the vocabulary as a complete word. But the other words is kind of a Hindi word written in English. So there are high chance that this model will not have these words as a in its vocabulary, and might be it's creating when uh, tokenizing its words, it will be creating n-gram tokens of these words instead of the complete tokens. So let's test this our hypothesis. So what I did, like, just from the same embedding model underscore tokenizer dot tokenize, so it will just create a tokenizer of these words. Like, I just pass these three words, and if you see, yeah, so for these two Samagra, Shiksha, it's uh, creating n grams instead of giving complete, but for a script it just gave the complete word. So now what is happening, the embedding what we are creating for this query, the majority of importance is going to the complete word scheme, and these words which are n grams don't have much say, and that's why whatever chunks we are getting in back, uh, they they would be more driven by this scheme token than these other tokens. And you can see also, if you search scheme and see how many scheme words are there in your chunks, if you see all the three chunks have good number of scheme as a word there. So that's why we are getting these chunks retrieved. So now, so our hypothesis was right, and now we'll see like what could be the solution for, like, how we can fix this issue. So I think there are multiple ways we can do it. So either increase the number of context retrieve, like instead of top k we set 3, we can set a bigger value like top 5, top 6, so that we can get that context also. Or secondly, we can just reduce the chunk size. So currently we have created a chunk size of 512. Now the whatever embedding we are getting, it has a information of all 500 tokens. So if you just create a smaller chunk size, the embedding quality would be high, and if that word has these anagrams also, they would have bigger say than available in 512 tokens. So that could be one way. And the third is like do a hybrid search, where you do a sparse search and then search together. But this is not part of this tutorial. I will just cover in next section or in further sections, like how we can do this hybrid search also. So here uh, we will be doing this second option, where we'll just try to reduce the chunk size and see how we get the performance. But I think the ideal what we want to do is, like, we always want to search our query on smaller chunks, but in return we want to give LLM the bigger context so that it can have more information to answer the question. And that is partially can be achieved through hierarchical node parser plus auto merging retriever, and that's what we'll look into next. So hierarchical node parser, what it does, like, you just give so instead of giving one chunk size, you give a list of chunk size. So what it will do, it will first create a chunks of 2048, and for every 2048 parent node, it will create sub nodes, like sub childs of 512 tokens for the same text. And for every 512 node, it will again create a child of 256. So it will store all this information, like root node, then top level node, then the second level node, and third level node. So top level node will have a chunk size of 204, right? Then it will have a child which has a chunk size of 512, and the third level child will have a chunk size of 256. And what we do is like we query the like we store this these leaf nodes and our vector store, so that when the query comes, we just query on these smaller chunks and find out the smaller chunks. And and there is a logic like which is done by AutoMergingRetriever, is like it will try to group multiple childs into one, and instead of giving multiple childs as a context, it will give you the parent node as a context. So we'll explain later, but yeah, so let's debug, like deep dive deeper into this hierarchical node parser. So you just create this instance by passing the list and chunk overlap of 20, and then same method, you get nodes from document, pass the complete document what we had, and it will create the hierarchical nodes. Now let's investigate how this hierarchical node works. So first what we'll do is like I'm just printing the hierarchical node at index 1, what the text it has, and I'm just splitting to see what is the length we got and also the text. So you see the length is 714. So first parent node is a size of 714, and this is the complete text or the first chunk it has created. Now what we'll do, we'll see how many childs are there for this node. So hierarchical nodes 1 dot child nodes, it will give you that it has 3 child nodes. So for this 714 chunk, it has created 3 different childs, and let's see what are the 3 different childs. So what we'll do, I'll just write a helper function which will just iterate through the nodes, and I'm just, for this node, I'm the finding the child nodes and then getting its node ID, and then matching with the full like iterating through all the nodes and matching with this node ID, and then printing wherever there's a match, and that is the child node. So if you see the first child is at index 22, it has a length of 327, and this is a text. So if you see millets places the use of millets, and if you see the first set, same places the use of millets. So what is, so same chunk the in the child we just create like a sub chunks of size lesser, like 512. So like first chunk is 327, chunk is second is 325, and the third one is 78. And if you see, it's ending at Dubai Expo, this word, and here also you will find the same Dubai Expo. So what it does is created a first node, bigger node of 2048. It divides the same node into 3 different child nodes of size less than 512, and it keeps a mapping. And the third what we'll check is like, let's take the first child node. So like this child node I will take and see how many other child node it created with a size of less than 256. So I'm just passing this, and again printing all the childs. So if you see, first child is size of 157, and again the same text is there, places the millets is, and the second child is size 154, and third child is of size only 17. So nitrogen from the atmosphere is the last thing word, so you should find the same thing in this nitrogen from the atmosphere. So similarly, like for this child node, it has created 3 different childs. It will do for this also, and it will do for this also. So in this way, it will create like a tree kind of structure where the parent node, the child node, and the leaf node would be there. So this is how this hierarchical node parser works. So it creates this mapping and it stores this information. So now what we'll do, we'll just take all the leaf nodes, because I want to search on the smallest chunk only, or the smallest context. And so what we'll do is just store the, we'll create an instance of this simple document to store, where we'll store all the hierarchical nodes. So all the complete nodes information is stored here, and I will just store them into storage context. From there it will be referenced back. Now I'm creating vector store index, but if you see here, I'm just passing the leaf node. So I'm not passing all the nodes, I'm just passing the leaf nodes, because I want that vector store should store the embedding of all the smallest nodes what we have, or the leaf nodes what we have, so that when the query comes, we are doing a cosine similarity on this smaller chunks. And then, so this is my base index. Now how from like by on querying the smallest chunk and getting the bigger chunk, how this everything happens is because of this auto merging retriever. So what it does, it looks at a set of leaf nodes and recurrency merges subsets of leaf node that reference the parent node beyond a given threshold. This allows us to consolidate potentially disparate smaller context into larger context that might help synthesis. So in simple terms, what it does is like it will first find all the based on this base index it on the query, it will find what all the matching child nodes are there. And if a child node, like for a parent node, if we got more than 50% as the child node in my context, so it will merge all those child nodes, like instead of giving those child node, it will give me the parent node. So currently it uses the threshold of 0.5. You can change the threshold. So what I'm doing is like I'm using the base index as a retriever, which is defined here, and I'm saying give me the top 3 matching leaf nodes. Now this base retriever is passed to this auto merging retriever, where it will see what all the leaf nodes I got for a given uh, parent node. If I got more than 50%, like suppose one parent node has 3 leaf nodes, and if I got 2 leaf nodes in my context, so what it will do is it will just merge them and it will give me the parent node text instead of giving me 2 child node text. And so we are creating instance of this auto merging retriever as a retriever, and then I'm just passing this into retriever query engine. So what it will do, it will take a query, it will pass through this retriever, and it will use the same uh, service content which has the embedding model and the large language model. So now this is the query engine where we can do a query. So I'll do just query engine dot query, passing all the questions there, and we'll see what all answers we are getting. We are getting all 5 correct. Let's see. So first is correct, like India is the largest. Second is, yeah, it got it correct, like Samagra Shiksha scheme is centrally sponsored scheme. This, so it has get this also correct. Third is also correct. Sickle cell anemia. Fourth is also correct, and the fifth one is also correct. So just creating this hierarchical node parser, we're just querying all the smallest chunk, and automatically auto merging decides whether it needs to give the smaller chunk only, or the parent node to the large language model. That is being decided by this. It has just improved our performance drastically. So uh, so next, what we'll just quickly check like how whether we really got that context or not. So like for this question one, so I'm just doing retriever dot retrieve, passing this question one to get all the context, and that's the same alpha function which will check whether this word is there or not. So yes, on the first context only this word is there. So if you see, this is the uh, uh, token where it mentions our Shiksha scheme. So this is the leaf node where we have this information. And if you have seen, like out of all the, like for all the 5 questions, there are only one instance where our auto merging retriever felt that it should merge the child node into parent node, because for this only we got multiple more than 50% of child nodes of this parent node only, and that's why I said okay, instead of returning the child node, let's me give back the parent node only. So yeah, that's all we have for today, where we see how we can start from building from basic rack pipeline to the advanced rack pipeline, which performs pretty well. You can test the performance more thoroughly. I just tested quickly, but I will be doing more thoroughly. You can also check and see if something is picking or not picking. And In the next session we'll see like what is the limitation of this auto merging retriever, and can we design something which is better than this. So thank you, and please feel free to share your feedback and the comments, and do subscribe my channel.